So today I will talk about serpentinized faults and related seismicity. So I will talk about many different papers that I have worked on since my PhD. And so I will talk both about directly triggered seismicity related to serpentinized faults and indirectly triggered seismicity. Next slide, please. So first, of course, I have many people to thank. All of these, all of the presented works are not only my work, but a collaboration with many people in transdisciplinary cooperation. Next slide, please. The double Weda-Tibenov structures has been found by quite a while ago by Hasegawa in 1978. This is the most famous, one of the most famous examples in northeast Japan. So the two planes are separated by 10 to 40 kilometers and tend to merge at depths. Next slide, please. The distance between the planes is related directly to the plate, the age of the plate, and the depth at which the planes merge can vary between 120 and 200 and something kilometer, depending on the velocity of the subduction and the age of the plate. So in this talk, I will focus on the lower Weda-Tibenov plane, which is contrary to the upper plane. Next slide, please. Contrary to the upper plane, next slide, the lower plane is located totally in the mantle, and so we can make the assumption, at least for the experiments we've done, we can make the assumption that it is mostly peridotite and thus mostly olivine. Next slide, please. When we add when water is added to olivine or to peridotites, serpentine minerals are formed, and so here is the structure of the antigerite, which is the high temperature serpentine variety. And this is just to show that compared to the olivine structure that was shown at the previous slide, that basically all the atoms have to find a way to move, and that it's not possible to transform to dehydrate serpentine without significantly reducing the grain size. Next slide, please. And so usually we simplify the formula of serpentine minerals, considering the formula of chrysotile, but actually the formula can vary. You have many different kinds of antigerite minerals with the wavelengths, the M value that can vary between 13 and 24, even though some of them are not really found in nature or rarely found in nature. And the point is that they all have different stability limits, and they are all separated by a minor dehydration reaction. Next slide, please. So this is considering the antigerite with M equal 17. In a pressure temperature diagram, we can represent the stability limit of serpentine minerals, and so here, if we consider the depth range between 1 and 4 gigapascals, which corresponds more or less to the start and the merging depth of the lower Weda-Tibenov plane. We can see that we are supposed to have the dehydration of antigerite around 550 degrees, almost an isotherm. In the in the case of a system that is not saturated in water, and if we have water saturation, we have we expect dehydration at somehow a higher temperature between 600 and 650 degrees. And in one case, you will have the transient formation of talc-like phases, and on the but if the system is saturated in water, we don't expect this phase to form, and we directly form olivine, enstatite, and water. Next slide, please. And this is the an additional reaction that is actually quite important. That is the dehydration of the, I mean, this is the transformation of the, I mean, the reaction between antigerite and brucite, so which is magnesium hydroxide. And you will see that it fits quite well some seismicity. Next slide, please. So this is the, after the work of Abers 2013, the pressure temperature conditions at hypocenters for earthquakes of the lower Wedatibenov plain beneath Tohoku. Next slide, please. Same for Hokkaido. Next slide, please. 3 next slides. Cascadia, Tokai, and Kii. Tokai and Kii being parts of the Nankai Trench. So as you can see, we don't have the seismicity following the lines of the stability limits of minerals in the magnesium, silicium, hydrogen system, which is a simplified view of nature. But the seismicity seem to start at least after some of these lines, or to increase, but it's only partly satisfactory. Next slide, please. So how did we trigger intermediate depth mantle earthquakes? Next slide. So we took San Carlos olivine and Corsica antigerite, which is considered as, I mean, which is known as a relatively homogeneous antigerite, and we can have it in quite large quantities. Next slide, please. We could cook fine-grained samples during 10 hours at 500 degrees in 1.5 gigapascals to get samples for synchrotron experiments with a different amount of serpentine. Next slide, please. So we did high pressure experiments in the DDIA apparatus. I can detail this later if someone wants. Next slide, please. So we used the X-ray to deduce, thanks to the diffraction of X-rays, we had the elastic strain of as seen by the olivine grains, and thanks to the X-ray, not tomography, the absorption of the X-rays, we had the displacement, because we had the gold foils on top and bottom of the sample, and we have the acoustic receivers beneath each of the sample of the anvil holders. Next slide, please. So this is the result of an experiment at 1.1 GPa. So you have the stress in olivine as a function of strain, and the cumulative number of acoustic emissions as a function of strain. As you can see, when you push on the sample, you increase the stress, and when you increase the temperature, which is in gray, you decrease the stress. And so this is a boring experiment, but important. Next slide, please. Same situation with 5% of serpentine in the sample, and you see that even though overall the stress level in the sample is lower, we have a significant amount of acoustic activity once we reach the stability limit of antigerite. Next slide, please. So same experiment with 20% of serpentine and a totally silent experiment. Next slide, please. So these are the other set of experiments at 3.5 GPa. So you see that we have acoustic activity in any case, and importantly, we have a large stress drop both in the blue and red curves. But in the blue curve is because we reach a very high differential stress at the samples scale, which is about 3 GPa. But in the red curve, so with 50% of antiquarite, we have a stress drop during the dehydration, which means that we have a full connection of the serpentine network from top to bottom of the sample. Next slide, please. So this is a summary of the experiments. So we at 1.1 GPa, we have acoustic activity only with 5% serpentine, and only once we are outside the stability field of serpentine. At higher pressure, we have dynamic rupture developing with any amount of antiquarite, and during all the potential instability of serpentine. Next slide, please. This is just a comparison with the natural seismicity that I was showing before. And one important thing is to keep in mind that we have the positive Clapeyron slope of the reaction at 1 GPa and the negative at 4 GPa. Next slide, please. So it's a very simple way to summarize the situation. When you increase the fraction of serpentine, you increase the length of the serpentine clusters, but you decrease the scale of the what I call the asperity, which is the antiquarite free volumes, the elastic olivine skeleton of the sample. Next slide, please. So this was the paper published in Nature Communications in 2017. So you have a length as a function of the antiquarite fraction. You have the cluster length in red, the asperity length in black, and the fraction nucleation length. So you can check the work of Onaka 2003, for example, explaining what is the fracture nucleation length. This is basically a rupture criterion as a length, expressed as a length. It's the length at which rupture accelerates and until becoming unstable, and then you have this competition, this process of the dynamic, the seismic rupture that occurs when you have this conflict between the rupture velocity and the sliding velocity that actually make the system impossible to propagate silently, I would say. And importantly, this fraction nucleation length significantly decrease when you increase the shear stress. So it's supposed to decrease with pressure. And so this is the dehydration-driven stress transfer model. This is not related to volume change. This is not related to any fluid over pressure. So this is not dehydration embrittlement. And so I would appreciate if this is well cited in the future, because sometimes it's not, because I don't want my name to be associated with the model that I contradict in a way. But we can discuss it later. Next slide, please. So as one of the the best consequence of these experiments is actually that we found this micro pseudotachelite. Next slide, please. So this you can see the fault that is here. Next slide. Next slide. So the fault is 1 millimeter long. The displacement on the fault is 10 micrometer, and you have features that you can see on the figure C that seem to be branched on the fault. Next slide, please. When we do transmission electron microscopy next to the fault, but I mean not on the fault, we have the dehydration products, olivine, talc-like, fluid vesicles. Next slide, please. On the fault, we can see that the fault thickness is between 20 and 200 nanometer on average, and you have these amorphous pockets with vesicles. Next slide, please. And in the features that is branched on the fault, we have euhedral olivine, and so this is the demonstration that this comes from the solidification of a liquid, silicate liquid. So this is in microsurotachelite. Next slide, please. Next slide. So as a reminder, the rupture is expected to break volumes in between the pre-existing serpentinized faults, but we don't expect these ruptures to actually follow the pre-existing faults. It's not about reactivating. It doesn't mean that you cannot have also some events, especially some events located in between the lower plane and the upper plane, that can actually be due to local reactivation of some of these faults. But for the lower plane of seismicity, what we are rupturing is the fresh peridotite volumes in between. Next slide, please. And regarding the relative silence in between the planes, this is because you have too much connectivity of the serpentine or other minerals actually that are quite weak. And so if you don't have the explosive, because a bomb is an explosive plus a detonator, an earthquake is elastic energy stored in basically in the fresh peridotite volumes, plus local instability due to a transformation, for example. And so if you don't have the explosive, you don't have seismicity. Next slide, please. So this was the beginning of the transdisciplinary journey. I will try to go quick. Next slide, please. In various massifs of ultramafic rocks, you can find pseudotachelites in the fresh peridotite bodies, and you cannot see them propagating outside in the serpentine. I would say that is around these bodies. Next slide, please. Now I will show quickly an equivalent in Balmuchia, even though it's not a subduction zone, but still. Next slide, please. So in this paper, next slide, please, we have studied this fault. So this is the magnitude 6 earthquakes. The fault is 5 millimeters thick, and the displacement on it 1.7 meter. Next slide, please. And you have this large injection vein of 15 cubic meter. Part of it are actually blocks of peridotite. Next slide, please. I compared this natural earthquakes of magnitude 6 with the experimental earthquakes of magnitude -6 that I was showing previously, because I wanted to see if they are totally representative of each other. And this is more or less the case, but there is something important to discuss. Next slide, please. So it motivated me to find data about displacement and fault thickness, pseudotachelite thickness in the literature. And so this is all what I found. So you have the natural examples, you have the D-dia experiments, the six-slip experiments, the rotary shear experiments. You can find it in the 2021 GGR paper. Next slide, please. Next slide, please. And so what we found, I mean, if we try to find a way to propose a scaling law, because the adiabatic assumption was not enough, and so we modeled it as a Stefan problem. So this is the heat balance at the advancing melt front, and so for each increment of a temperature increase by shearing at the tip of the crack, you have a temperature decrease by thermal diffusion. And also, I mean, and most of the thermal diffusion is controlled by the opening of the tension crack on one side of the fault. That is actually sucking the lubricant, basically the magma out of the fault core, and it goes in a volume that is 1,000, at least 1,000 degrees lower in in temperature. And so one of the consequences of this work is that we showed that there is a critical length at which the scaling is not the scaling at a small scale is not relevant, totally relevant, because something happens at a large scale that makes the lubricant very efficient. There is a length at which um, the magma layer is actually able to totally decouple the system. Next slide, please. Next slide, please. So I continued. So I did this comparison. Next slide, please. And I also compared. I did interdisciplinary study with Saiko Kita. Next slide, please. So in this work, we selected the seismicity of the lower Wada-Benioff plane. Next slide, please. And we noticed that the B value, so the slope of the Gutenberg-Richter distribution, was much higher in the lower plane. Next slide, please. And we so we tried to check in the why this was so high in almost one in the lower plane compared to in Benistohoku compared to Hokkaido. Next slide, please. And actually, when checking the experimental B values, we found that it's the same in the samples. When you increase the serpentine fraction, you increase the B value. So it means you decrease, you increase the you distribute the seismic events in many small events compared to some large events. Next slide, please. So which means that the pre-existing faults, the serpentinized faults that exist in the Japan slab are much denser, have a denser distribution compared to the Hokkaido, the Kuril slab. Next slide, please. Next slide, please. Sorry, so importantly, the lower Wada-Benioff plane was supposed to be an isotherm of dehydration of serpentine, but actually it's not. It's located somewhere between 600 degrees and 800 degrees, but it is, as far as I understood, and consistently with everything that I showed before, it is the souvenir of the brittle ductile transition of the oceanic plate. So this is where the serpentinized faults were rooting before subduction. And so, and this is also, I mean, what Ranero predicted in 2003. Next slide, please. Next slide, please. I will skip this. I will skip this as well. So as I said earlier, we don't have this. We don't have the simple MSH system. Next slide, please. We don't have this either. So we don't have this either. You see, it's not. So we can make the system complex, but it will never be. I mean, any simplification we will make, this is just the MASH system. So we just added aluminum, and we added the possibility of fluid saturation or fluid under saturation. But still, we cannot reproduce the entire seismicity. Next slide, please. And so it's, in my opinion, it's because there are many phases that we don't know exactly the stability, or some phases that we actually don't know, we have not discovered yet. I'm thinking about the talc-like phases. Next slide, please. This is, as an example, all the experimental data we have on antichorite only, depending on if we have some composition differences or saturation differences. And so we can already reproduce 90% of the seismicity of the lower Wada-Benioff planes. Next slide, please. These are the other serpentine minerals. Next slide, please. And chlorite and chloritoid minerals. I know chloritoid here is not expected, but locally, if you have some metasomatism, why not? Next slide, please. This is an example for northern Chile, and you can see that especially the large seismic cloud at 100 kilometer fits quite well with the pressure-induced dehydration of serpentine plus brucite. Next slide, please. And I will try to go very fast. Next slide, please. So in Romania, we have an equivalent. So this is not an active subduction. Next slide, please. But so this is so I deleted the slide that was important. Anyways, so I made a pressure temperature diagram, and I showed that it is actually a serpentine dehydration that triggers this seismicity, and also talc-like or phase A dehydration at higher pressure depths. And also we have an apparent slab pool in the slab in between 80 and 120 kilometer, and I think it's only due to the negative volume change and full fluid circulation. So this is not published. This one is not published yet. Sorry for the mistake. Next slide, please. Next slide, please. Yep. So, and this is the pressure temperature diagram I was talking about. Sorry, the slide was deleted. Next slide, please. And so very quick, so I was talking about the intermediate depth earthquakes. Next slide, please. Now we talk about the deep earthquakes for 1 minute. Next slide, please. So in Japan, so thanks to a machine learning algorithm, we have found that the water, the hydration level of the plate before subduction was actually controlling the distribution of the seismicity, of the deep seismicity, so above 350 kilometer depth. We found that at the magnitude 3.7 or 3.8, and for events that are smaller than this magnitude, you have a much larger seismicity in the regions of Izu and Honshu compared to Kuril and Bonin. And we read this. We propose that this is triggered by the presence, the larger presence of hydrous defects within olivine in these segments of the Pacific plate. Next slide, please. And so this magnitude of 3.8 is about less than 1 kilometer, and so this would be the thickness of the unstable rim around the metastable olivine wedge. And this other magnitude, I mean the 10 kilometer of the full thickness of this wedge actually corresponds to the magnitude of 6.7 that was found by Tsan in 2017 using the full CMT catalog. Next slide, please. Next slide, please. Very quickly, so some other topics that I'm currently working on. Next slide, please. And thank you for your attention, and I hope you have some questions. Sorry, I went a bit too fast in the end of this talk.
Okay, yeah, so good morning for me here in Calgary, and good afternoon, evening for those of you in Europe. It's I'm going to talk about Mars today and Martian serpentinization. I just looked at the recent measurements of temperature at Gale Crater by the Curiosity rover, and our high today in Calgary of -21 Celsius is lower than the high that Curiosity has been experiencing at Gale. So it's colder here than it is on Mars. So I want to, at that same time, mention that although I am part of the Curiosity rover team, all of this work was conducted parallel to or outside of the Curiosity rover mission. So nothing that I say today is coming out of Curiosity results, the Mars Science Laboratory. And while I'm here, I also want to acknowledge co-author Nick Tosca, who worked with me on this project over many years now, and hopefully it'll hopefully be published soon. So I want to talk about habitability, right? So habitability is this thing that we all say, maybe a word that you've said, maybe you've heard in terms of planetary processes. But what is it that creates habitability? And so there's this really nice diagram here by Tori Holler in 2007 that says you need to somehow bring together the ingredients, the energy, the solvent, water, and the conditions all together in the same place at the same time to make a habitable environment. So I really want to focus on a process that can generate habitable environments on planetary surfaces, which you all know is serpentinization. So we have abundant evidence now from the numerous rovers on Mars, as well as orbital measurements, that Mars used to be warm and wet. So we have this really nice paper from Robin Wordsworth in 2021 that suggests that sometime in its distant past, probably before 3 billion years ago, there was flowing water on the surface. And we see that in terms of, as evidenced in aqueous geomorphology features, valley networks, and crater degradation, as well as basin lake formation, as well as the things that many of us as serpentinization scientists think about, aqueous geochemistry, so abundant phyllosilicates in the Noachian, sulfates and evaporates, manganese oxides, all of which seem to require the presence of liquid water on the surface of the planet in order for them to exist. And in this paper, there's also this really nice plot of the time, the millions of years that the planetary surface of Mars was warm, above freezing, basically, as a function of its history. So from the planet's beginning to present, and then there's you see a step function here increasing through time, and so it seems to have reached its maximum number of years of warmness by about 3.5 billion years ago. And of course, the variations here are the partial pressures of CO2, but there's something else that's happening that give you these step functions early on in the planetary history, and that's what we're going to talk about today. Specifically, they point to the abundance of oxidizing versus reducing atmospheres on the early planet that would enable a greenhouse effect that could then warm its surface and create the water that then contributes to the production of phyllosilicate minerals, sulfates and evaporites, manganese oxides, as well as all those geomorphology features. So you see that these blue spikes where the blues come above the reds, that's when the atmosphere is reducing. It's rich in hydrogen, perhaps methane and other reducing gases. Those are together a strong greenhouse, and they then create warming conditions on the planet. And those are what contribute to that step function early on in Mars history. So simply put, from the Wordsworth et al. Paper, a warm, wet early Mars apparently needed hydrogen to trap heat. And how do planets trap or make hydrogen? Of course, we all know that. We're here at the SerpentineDays webinar series. Serpentinization is a primary process by which planets make hydrogen. And so those of you that have thought about Mars and thought about serpentinization have probably come across this paper at some point in your studies. And you'll see that orbital spectroscopy measurements here collected by Bethany Ellman and others back in 2010 suggest that there's not much serpentine, and I have that in quotes here, and that's really something that we're going to really get into today on the Martian surface. So each one of these stars here are definitive identifications of serpentine on the Martian surface. The squares are probable identifications of serpentine. And then all of these black places are places, or black dots are places where they looked but did not find serpentine. So sad emoji for those of us that love serpentine, right? There's not apparently too much of it on the serpentine or on the Martian surface. But I hope today to discuss a potential alternative to this, that perhaps Mars produced a different form of serpentine than is commonly looked for in spectroscopy data sets, and hopefully that would then help to indicate how the early planet produced so much hydrogen and had such a warming atmosphere. So what is serpentinization? I'm really preaching to the choir here, so I can go through this quite quickly. So serpentinization is common on planetary surfaces. It adds water to olivine, oxidizes iron, and produces hydrogen. So here is this beautiful dunite here. So this mantle peridotite. To that, we can add some water. So this is a beaker of water here, and it's exactly 1.4 or 1.3 liters, because this rock here, this is an exhibit in the Smithsonian. I encourage you all to see it if you're ever in Washington, D.C. That contains exactly this much water. So this rock contains 12.5% water by weight. And so this rock used to be nominally anhydrous, completely olivine rich with accessory minerals, and now is completely serpentinized and containing serpentine, brucite, and magnetite. So again, serpentinization adds water to olivine, oxidizes iron, and produces hydrogen. So this is a classic plot. These are data from Mayhew and others, 2020, that I have obviously left the citation off of, but it will show up eventually. And so here we have on the x-axis loss of ignition or water weight percent, but what you can think of that as is the serpentinization degree, right? So as we go from 0% water or loss on ignition to around 13.5% water or loss on ignition, we go from 0% serpentinized to 100% serpentinized. And then on the x-axis or the y-axis, we're going from 0% oxidized iron to more like 60 to 90% oxidized iron. So that's the iron oxidation function. So I'm going to show a series of plots here that all have sort of those same axes as we go. So again, we start here with this nominally anhydrous rock, and we produce serpentine minerals here, magnetite. And since all of the iron began as Fe2 plus and has become oxidized, we generate hydrogen during that process. And what we can do, and this will become important or more relevant in a minute, what we can do is take that and not just have it normalized by the total iron, we can actually just calculate the iron weight percent, and Mayhew and others did this in 2020. And what you can do with that number is by assuming that all of the iron was initially Fe2 plus and calculate based on that hydrogen production, you can get on the other y-axis here, the moles of hydrogen that is generated per kilogram of rock. And you can see that you expect on the order of about 0.3 moles or so of hydrogen per kilogram of rock that gets completely serpentinized. But importantly, Lisa's data set there, I think, is mostly focused on terrestrial serpentinites, what we would classically think of as serpentinization of FO90 olivine and its conversion to magnetite and serpentine and perhaps brucite. And so Earth's mantle is typically made up of this beautiful green olivine here. Those of us who looked at San Carlos olivine, gem quality olivine, it's always this beautiful apple green color. Peridotite is the gemstone. But many of us have been in rock shops and have seen these things as well on the right-hand side, palisite meteorites, right? And the olivine in those rocks is much more iron rich. It contains much more iron. And therefore, if it is going to go through that same process of water addition and iron oxidation, it's not going to produce the same amount of hydrogen. So not all serpentinization will produce equal hydrogen. So simply put, Olivines of Earth's mantle contain very little iron. And so here's the terrestrial mantle plotted here on this solid solution diagram between forsterite here at high silica, low magnesium or low iron, so 0 iron is forsterite, and then the phaelite end member plotting up here. So you see that the terrestrial mantle, of course, at about FO90 or 91, plots very close to the forsterite end member. The question then, if we want to think about serpentinization on Mars, is how do Martian olivines compare to these terrestrial mantle olivines? Fortunately, Curiosity rover has analyzed olivines in situ on Mars using the ChemIn X-ray diffraction instrument. And so this is an animation of the ChemIn instrument. So essentially what Curiosity does is it drills a sample, pops it into its belly, and then it runs powder X-ray diffraction using the ChemIn instrument to determine the mineralogy. And using Rietveld refinement, it can determine very accurately the FO number of the olivines. And of course, as you probably expect, from the fact that it is the red planet, right, it is covered in iron, the olivines in Gale Crater are all significantly more iron enriched than the terrestrial mantle. So so far, olivine has been discovered in 4 samples in Gale Crater, and each one of those is significantly more enriched in iron relative to the terrestrial mantle. We can also go and collect all of the electron microprobe analyses and wet chemistry analyses of olivines in the Martian meteorites. And you see, again, that all of those span this range that is much more iron rich than the terrestrial mantle. And we can group those into two different classes of meteorites: the olivine-rich meteorites, olivine and orthopyroxene ferric and larzolitic shergottites and dunites, and the olivine-poor ones, the basaltic shergottites and the clinopyroxenites. And so if we want to look at serpentinization reactions, we really want to think of these olivine-rich sort of ultramafic rocks here, again, that are very similar in chemistry to those ones that have been analyzed in Gale Crater. So if we want to understand serpentinization on Mars, we have to understand serpentinization processes in rocks that are very different from the terrestrial mantle. We have to understand anomalous serpentinites on Earth, ones that we're not used to looking at in the mantle or derived from the mantle. Where can we find those? We found those in ultramafic layered intrusions, such as the Duluth Complex in Minnesota in the United States. And so these blue dots here are all olivines from the Duluth Complex, and you see that they very nicely overlap with all of those olivines that have been analyzed by Curiosity and Gale, and most of the range of the olivine-rich meteorites in general. So again, if we study serpentinization of these Duluth Complex olivines, we might have a better chance of understanding serpentinization on Mars. So here's the Duluth Complex. The Duluth Complex, again, occurs in northern Minnesota, south of Canada here. And so it's these yellow layers here on the sort of the basal part of the complex, known as the troctolitic series. Those are the rocks that contain these olivine enriched units. And here, as on the title slide of my talk, is one of those serpentinites. And you immediately, if you've ever looked at a serpentinite under the microscope, you'll see something very different about this rock, and it's that the serpentine is really brown. And the serpentine is really brown because it contains a ton of iron compared to the normal terrestrial mantle serpentinites that we're used to looking at. And so if we are able to study these serpentinites of the Duluth Complex, we might be able to understand how hydrogen greenhouse was generated on early Mars. And fortunately for us, the Duluth Complex has been studied for a very long time. While I was researching this paper, I found this really nice paper from 1918 by Grout and others. And so the Duluth Gabbro, as it was called at that time, is actually these rocks. And so you'll notice the similarity in the shape of this rock series here, and those olivine-rich rocks are on the outside. And note, even then we knew that these rocks of the Gabbro series can be classified as normal Gabbro, olivine gabbro, and then troctolite and peridotite, which are the rocks that we focus on in order to understand serpentinites. And so there is a lot of olivine in this rock. And so I was looking at this figure on the left-hand side from the 1918 Grout paper, and I read this closely, and it says the dark areas are olivine crystals, right? And that's a rock hammer, and unless that's a toy hammer, those are some gigantic crystals of pleistoclitic olivine. I've never seen anything like that in the field. Typically, what we see in the field is on the right-hand side here, where you do have rhythmic layering of olivine-enriched and olivine-poor units overlaid with sometimes dikes and fractures into there. And again, I just needed to show this because this is one of my favorite versions of pre-Excel or pre-Illustrator plotting of scientific data. And what you see here is the diagram of the norms of the analyses of the Gabbro at Duluth. And this row here with the large pinnacle in the back here is the olivine row. And so you see that some of these rocks are extraordinarily enriched in olivine, and some of them have very little olivine in them. Okay, so going back to the Mayhew and others plots here, on the left-hand side again is oxidized over total iron as a function of serpentinization progress, and on the right-hand side is the total weight percent, so no longer normalized by total iron, and then the hydrogen production. And so if I could then turn those gray here, that's Mayhew's data turned gray, and then I overlay with that a bunch of bulk rock analyses of serpentinites from the Duluth Complex, what you see is actually a very similar trend, where we are increasing the proportion of oxidized iron as a function of reaction progress, basically completely in line with the trend that is coming out of the rocks from the terrestrial mantle. So as my high school history teacher used to say, the more things change, the more they stay the same, right? So we get exactly the same progress of ratio iron oxidized over iron total as a function of reaction progress. However, if we then go and do the same analysis, but now we're looking at oxidized iron weight percent as a function of water addition, we see a very different trend. And so what this shows us is that these rocks produce about 5 times more hydrogen per degree of serpentinization than rocks from the terrestrial mantle. And I think that's a really quite profound result that we then need to consider if we're going to try to understand serpentinization on Mars. So what exactly is happening here? We can then go and look in more fine detail at what the mineralogy of these serpentinites looks like. So hydrogen is produced as magnetite and iron, oxidized iron grow, and so we could show that specifically using measurements. So there's 3 ways that we can get oxidized iron into serpentine crystallographically. So this is just the lizardite structure. We can consider antigerite and chrysotile as being similar, although not identical to this. And what we can do is somehow substitute in oxidized iron for magnesiums or silicons in the octahedral and tetrahedral sheets. So we have 3 ways of doing this. First is the dioctahedral substitution. 2 oxidized irons for 3 magnesium 2 pluses. So that's a 6 for 6 substitution towards this mineral, hissingerite. So it's got a vacancy and it has 2 oxidized irons in the octahedral sheet, no oxidized iron in the tetrahedral sheet. And so we studied that with Bernard Evans in this minerals paper in 2019. Deprotonation reaction. So this was primarily advocated by Vodnikov in 2005. I don't see much evidence for this in many rocks, including in their analyses, but I won't get into that today. So let's just not consider deprotonation as a really major reaction that generates oxidized iron. And the third one is Ferri-Tschermaks substitution. So in this case, we maintain charge balance by substituting 2 oxidized irons for a magnesium in the octahedral sheet and a silicon in the tetrahedral sheet, which could make a reaction towards or a vector towards the magnesium kronstadtite mineral shown here. So we published a paper, Nick Tosca, Bill Seafried, and I, a couple of years ago in PNAS, where we really explored this Ferri-Tschermaks substitution. And that is the process that's dominant in terrestrial serpentinites. And so what we show there is that we are depleting silicon in the structure. So again, that's oxidized iron substitution for silicon in the tetrahedral sheet. And we show that using Mossbauer spectroscopy, which is not shown here, thermodynamic and theoretical calculations, which is shown here, and then also electron microprobe data shown on the right-hand side. So that is the dominant mechanism for oxidized iron incorporation into terrestrial serpentinites. And you might expect that that might be similar on Mars, but our results tend to disagree with that. So the dioctahedral substitution mechanism, actually, this towards hissingerite end member is substitution is dominant in Duluth serpentinites. And we can show that here in 2 ways. So in these rocks, the iron is so enriched in the serpentines that we can actually use a diagram like this in order to study oxidized iron generation in the serpentine structure. So what I have plotted here is silica over total cations on the y-axis and iron number essentially on the x-axis. And we go from magnesium serpentine, so that's lizardite, chrysotile, or antigerite, to hissingerite at the top here, so that's all oxidized iron in the octahedral sheet, and green light here, all Fe2 plus in the octahedral sheet down here. And note, if we were to plot iron and magnesium kronstadtite on this plot, its ratio of silica over total cations is about 0.25, so it would plot down below the bottom of this grid here. So if we then go and take a whole bunch of electron microprobes, so 93 electron microprobe analyses of Duluth Complex serpentinites, we see this trend going from magnesium serpentine up towards hissingerite with relatively little or no green light component. And so this is just a kernel density estimate of all 93 of those points. And you see essentially that even though we've analyzed rocks from different parts of the complex, so they have different magnesium numbers because their protoliths olivines were different original magnesium numbers, you note that in all cases they're trending up towards hissingerite and towards having significant amounts of oxidized iron in their structure. And so we can then also go and do synchrotrons X-ray absorption near edge spectroscopy or ZANES measurements to try and get at the oxidized iron generation in the serpentine structure in a different way, so a more direct measurement of actual redox state rather than just based on crystallographic constraints, which the electron microprobe allows. And so here what I'm plotting is the integrated pre-edge intensity versus the pre-edge centroid energy. And so the important things to note is that if we have olivine or greenolite, it would plot down here in the lower left-hand corner. If we have Hissingerite, it would plot down here in the lower right-hand corner. And if we had Cronstedtite substitution, it would plot approximately halfway in between these two and probably on a trend between those two. Sorry, I just accidentally clicked forward, but that's fine. So if we look here, so I have a whole bunch of electron or X-ray absorption near-edge spectroscopy measurements here. And again, we did the kernel density estimate. And you see that the olivine, and if there is any iron 2+ serpentine, all clustered down here in the lower corner. Again, greater than 90% iron 2+. And then what we see from the kernel density estimate is that the majority of our serpentine analyses plot up here at the octahedral Fe3+. Again, consistent with Hissingerite formation as a function of reaction progress. If we then go and do bulk Mossbauer spectroscopy here on the analyses to get at how much of the oxidized iron in our bulk rock analyses is hosted in Hissingerite versus how much of it is hosted in magnetite, we can look at this plot here. And what we see is that if we look at the matrix, so this is serpentinization in sort of a mesh texture where you still have relict olivines around, we see that around half of the oxidized iron is in magnetite. If we then go to a fracture where there is no relict olivine at all, what we see again is that around 46%, so about half of the oxidized iron is in magnetite. Okay, so going back to this sad grimace emoji plot from the beginning, so even if Mars is only weakly serpentinized, we can say something new about this. Serpentinization likely played a significant role in its biogeochemical evolution. So even if it's only, let's say, 20% serpentinized, that would have produced 100% of the hydrogen as a fully oxidized or fully serpentinized peridotite here on Earth. However, if we then go and look specifically for Hissingerite in close association with magnetite on the Martian surface, we might be able to find more serpentine. So this plot here is a plot of the magnetic anomaly across the Martian surface. And so places of bright red are places of high magnetization. And then all of the circles here are spectra that would be consistent with either nontronite or Hissingerite, so have octahedral Fe3+. And what you see then is that in places where there's high magnetization and large amounts of these clustering of octahedral Fe3+ in phyllosilicates are probably places or potentially places that serpentinization would have occurred on the Asian Martian surface, and that if we were to explore them in more detail, we might find more evidence for serpentinization. So no longer sad emoji, we can now have the thinking emoji and perhaps go and explore this more. So what ultimately happened to the Martian surface? Why doesn't serpentinization continue to fuel a warm, wet Martian surface today? And that what has happened is ultimately that Mars's gravity is much lower than Earth's, and it also has a lack of magnetic field. And so what's happening is the solar wind is just constantly stripping its atmosphere off into space. So as we generate hydrogen, it ultimately then builds up in the atmosphere. Of course, the escape rate is proportional to the hydrogen concentration in the atmosphere. So as you build it up in higher proportions, it escapes even faster. And then ultimately that hydrogen escaped. So Mars then eventually permanently lost its reducing atmosphere and then never warmed again. And so that's why these plots in the Wordsworth model essentially hit a peak in the number of years above freezing and then have never returned again. Okay, so I just want to thank everyone, all of the funding organizations that funded this research and various previous forms of it, including the fieldwork way back when I was still a PhD student at the University of Minnesota. And I really want to point out that teamwork makes the dream work. Nick Tosca really was influential in bringing this all together.